Welcome to Ready to Derive. In this video, we are going to talk about the mean value theorem for integrals. Now, we've already met the mean value theorem for derivatives, which basically says that if you're on a road trip and your average speed is 60 miles an hour for the time of the trip, you must have been going at least one time at 60 miles an hour. You could have been on cruise control and going the whole time, but the mean value theorem guarantees at least one time. So the mean value theorem for integrals, well, I'm not going to give too much away because that's what this video is about. But one thing you do need to know going into this video is the formula for the average value of a function. And if we look at a function and there, that green line there, say, represents the calculation for the average value, the mean value theorem, just as a little preview for integrals, does also guarantee that there exists some value in the interval for which the function takes on the average value. So if you're not familiar with this formula, you might want to watch my video on average value of a function, which I'll link in the description. But without further ado, let's get started. So we're going to warm up by practicing finding the average value of a function. And in this particular context, a particle is moving along a horizontal line with that velocity function. We're going to find the average velocity of the particle over the time interval 0 to 3. So here's our average value formula customized to this velocity situation. And we are going to, so A and B is 3, so we'll do 1 over 3, A is 0. The area from 0 to, when I say area, so when I find the integral of the velocity function from 0 to 3, we're just finding the area under that velocity function. Okay, so that's going to be 1/3. Now let's find the antiderivative of this function. And this will be t squared, and this will be 3t. We're going to evaluate that antiderivative at 0 and 3. Now, notice that at 0, the antiderivative will be 0, so we only have to evaluate it at 3. 3 cubed minus 3 squared plus 3 times 3. And if you work that all out, you get an answer of 3. 3, whatever units the velocity units are, it could be meters per second or, feet per minute. So here we are. Here's a picture of the velocity, a graph of the velocity function. We can see that the velocity varies. It starts off at 3, and then it goes as low as 2, and then it steadily rises up into sort of maximum velocity of 6. So what does the average velocity mean? It means that on average, if this particle had just been traveling at constant speed, it would have gone at 3 units per whatever for the whole time period. So the average value or the average velocity just kind of averages out. And imagine if this particle just went at a constant velocity and for the whole time period. So a question you might ask in the scenario we're just considering is there a time in the interval 0 to 3 when the velocity of the particle equals the average velocity? Well, you can think about this sort of intuitively. How could the particle obviously probably is changing velocities over this time period. If it averages out to 3, how could there not be a time when its velocity was 3? It could have been maybe 2.8 at one moment and then 3.4 at another. It can't get from one velocity to the other without passing the average velocity at least once. So intuitively, it feels like this makes sense. Let's look for it algebraically. So here was the velocity function, and here was the average velocity of 3 that we calculated. So we want to find when they're equal. So let's just set them equal to each other. And we could subtract 3 from both sides, and then we get this. We could factor out t. And it appears that actually there are 2 times at which the velocity of the particle is equal to the average velocity. So let's look at this visually. So here is the average velocity of 3. And it looks like, indeed, there are 2 times, right? So when we sort of this point here and this point here is when the red curve intersects the green line. So that's at 0 and that's at 2. And so what this feels intuitively correct, this actually has a name. This is the mean value theorem for integrals, which we'll formalize in the next slide. So the mean value theorem for integrals is an example of an existence theorem, kind of like the mean value theorem for derivatives, the intermediate value theorem, the extreme value theorem. What existence theorems do is they guarantee that there exists a number in the interval along the x-axis that satisfies a certain equation. So in this case, we know that there must be a number c such that the value of the function at c equals the average value of the function over the interval ab. And let's just look at that visually and sort of label appropriately. So this is a, this is b, and if we extend this along here, this is the average value, but it's also now is the value of the function at some point c in the interval. So let's follow this along. Let's see there, where must that point be? This is where the average value of the function is actually equal to the value of the function at that point, which, there we go, is, in this case, is only one such point c, but there it exists. So it's basically saying that average value line must intersect the curve at least once. Now, if we take sort of another little interesting thing is if we take b minus a over here and cross multiply it, we get fc times b minus a. Now, what is that product? F of c is the average value over the length of the interval ab. So think of b minus a as really just the length of this interval. And if we cross multiply, then we get left with the integral from a to b of f of x alone. Well, what does that represent? That integral in red is really just the area under the curve. So the area under the function from a to b is equal to the area of the rectangle, which, because this is, let's label, so this height is f of c, and the width of that rectangle, the base, is just b minus a. So what in fact we're saying is there is a number c in the interval such that the rectangle with base ab and height fc has area equal to the area under the curve from a to b. And why does that make intuitive sense? Well, imagine if f was my velocity function, and I was on the highway. This is my velocity function. So if I found, and it's always positive, so I slow down, speed up, but I'm never going backwards. In this case, this quantity would give me the distance that I traveled over the time period a to b. Well, it makes sense that that distance could also be achieved by just taking my average value, my average velocity over that time interval. So that would be my average velocity, and that was the time I'm traveling for. And that's the whole point of averages. It makes the assumption I would have traveled the same distance if I'd just been on cruise control, going at my average velocity over that time period. That is the point of averages. So, all right, so now that we've formalized the mean value theorem for integrals, we will begin practice. So here's our first practice problem. And what I perhaps didn't emphasize enough in the last slide is that the function must be continuous on the interval for this to work. So 4 over x squared is only discontinuous at x equals 0. It's definitely continuous on the interval 1 to 4. So, and then why does that matter? Well, if you had a function and the average value of that function, say, was here, and that function happened to have an open circle right at that average value, we could see that at that average value, there is no c value. There is no point on the curve that would correspond to that. So the continuity condition is very important, otherwise it wouldn't hold. So we are going to find these values of c that are equal to the average value, and we have to start by finding the average value. So the interval, let's see, goes from 1 to 4. So the integral from 1 to 4, and I'm going to write 4x to the minus 2 like that to make it easier. I'm also going to bring that 4 outside of the integral. So this 4 here, I'm going to bring it outside, so get 4/3, and now I can take the antiderivative of just x to the minus 2, which is negative x to the minus 1 by the reverse power rule, and then we get 4/3. And we would get, if we plug in 4 and put it back down with our negative exponent, it's negative 1/4 minus negative 1 would become plus 1. And then that works out to be, if you do the math, you'll get 1 out as the answer. So let's have a look at that. So we have here, we found that the average value is 1, which is there, and we can sort of see it looks like at x equals 2 they intersect, but let's do part B properly now. So we're going to take the function. We want to find algebraically, is 4 over x squared ever equal to 1? Well, that's pretty straightforward. We can cross multiply and we get 4 equals x squared, which means x equals plus or minus 2, but negative 2 isn't here. So in this particular interval, we can say x, or we'll just use c for example. So x equals plus or minus 2 are the two answers, but in this interval, c equals 2. And so c equals 2, that's the value that the mean value theorem guarantees. And then just to kind of clarify again, because I love this area connection, don't forget that the area, the orange area there, is exactly equivalent to the area of that rectangle. For our second practice problem, we'll take a piecewise function like this. We don't have the equation for it, but we know we can figure out areas easily enough because we're dealing with triangles. And again, so let's start by finding the average value of this function. And we, let's see, we know that, b is all the way over there at 6, a is negative 2. And now we just need the area, the integral from a to b of f of x dx. We don't have an equation, so we're just going to have to go about it the old-fashioned way and find the area under the function all the way from negative 2 to 6. And this area is, this is a triangle whose base is 5 and whose height is 6. So that comes out to be 15. And then this here, now that's under the x-axis, so the area will be negative, and you can think of that as, well, the base is 3 and its height is negative 2, so in the negative direction, and that comes out to be negative 3. And 15 plus negative 3 is 12, so we know that we could replace this, well, let me write this first, negative 2 to 6, and that becomes 1/8 of that area we just figured out to be 12, and 12 divided by 8 is 1.5. And now in this case, to find the values of c, let's just put the line for 1.5 in there, the average value, and in this case we don't have the equation, so we are just going to identify where the curves intersect, or where the average value intersects the curve, and we have one here that looks about to be negative 1.5, and here maybe that's 2.25, and so we can end by saying that c equals negative 1.5 and 2.25. So there's two values at which it occurs, and one of the things, of that area under the curve, remember we found out it to be 12 if we do it just using geometry, and apparently 12, if we multiply the 8 over to the 1.5, is 8 times 1.5. And what is 1.5? 1.5, of course, is the height of this rectangle, and 8 is the base of this rectangle. And so the area of this is 8 times 1.5, which is 12, which is equivalent to the area under the orange function. So for our third practice problem, we're going to look at components of an AP Calculus AB problem, 2022, free response 1. And this is a calculator active question, so we may use our calculator. And A of t is a models the rate at which vehicles arrive at a toll plaza, and from 5 a.m. to 10 a.m. So part A asks this, right, but do not evaluate an integral expression that gives the total number of vehicles that arrive from 6 a.m. to 10 a.m. So that's from t equals 1 to t equals 5. I love these type of questions because you don't actually have to do any work. You just have to write the integral expression. So the total number of vehicles is the accumulation of vehicles, and the accumulation we know is always the area under the rate curve. So from 1, this time 1 to 5, and the rate is a of t dt. So we can write that on the AP exam. You don't have to replace a of t with its expression, that is sufficient. So that will give the total number of vehicles. And then we are asked in part B to find the average value of the rate in vehicles per hour. And well, we know that we would just take that area under the rate curve and we'd multiply it by 1 over b minus a. B is 5, a is 1. And but luckily we can do this in the calculator. You would never obviously be able to find the antiderivative of that complicated function. And we get 375.537 if we round to the third decimal place. So that is the average rate at which vehicles arrive in vehicles per hour. We don't have to round that to a whole number because average value can be a decimal. And now we're going to go on to a part C, which I kind of made myself to pertain to this video. So here is the part C that I modified. So we want to find the first time after 6 a.m. for which the rate at vehicles arrive is equal to the average rate. And again, we are going to do this by calculator, but I'm also going to take a moment to do this algebraically for one more practice problem, because it's kind of cool that you can solve this algebraically. So you'd set the rate function equal to the average value, and we want to find out when that happens. So let's just start solving. So divide by 450, and you get that this square root is equal to 0.8345. I'm going to go to 4 decimal places because 0.8 something is a smallish number. And to undo that, we're going to square both sides. If we do that, we get sine of 0.62t equals 0.6964. And then we're going to do inverse sine of both sides. Make sure you're in radian mode here, because if you're not, you won't get the correct answer. 6964, and that comes out to be 0.771. And then if we divide by 0.62, we get that t equals 1.243 hours. Now, luckily they asked for the first time, because we don't have to go and find any other values, because we know that, when you're dealing with inverse sine, there's other quadrants in which you can find answers to the same problem. So luckily this is the first time. And let's look at this. Let's look how we would do this in the calculator. So first of all, you'd graph. The pink graph is a of t, and the solid blue horizontal line is the average value. And if you haven't done this before, you would go to a second trace, which delivers you to the calculate menu, and you would select 5 for intersect. And it says first curve question mark. So you have to just select one of the curves close to the intersection point that you're interested in. And then it will jump when you hit enter, it will jump to the second curve, and you can see that one selected now. And then if you hit enter again, once you've selected the second curve, it's going to say guess. I don't know why they asked that, because you're not interested in guessing. You want them to figure it out, the calculator to figure it out. So you hit enter one more time, and you get that the intersection is indeed at the x value, or the time at which that occurs is when t is equal to 1.243 hours. So on this last slide, closing slide, I'm going to demonstrate a really interesting connection between the mean value theorem for derivatives and integrals. They kind of, in their essence, they're similar but very distinct. So here goes, just for a little summary. The mean value theorem for derivatives said that if you have a continuous and differentiable function on an interval a, b, and if you find that the slope of that yellow segment, a secant line, which is the average rate of change, right, f of b minus f of a over b minus a, then the mean value theorem for derivatives guarantees that there will be a value c at which the instantaneous rate of change is equal to the average rate of change. So at least one value, in this picture there's only one value of c for which that's true. Now, so the mean value theorem for derivatives says this about slopes, and let's see how this translates, it looks like, for integrals. So let's create the same graph. And the mean value theorem for integrals, of course, guarantees that there is some value c in the interval a to b, for which f of c, so the value at c, so f of c, the value of the function of c, is defined to be this, the average value, 1 over b minus a integral from a to b f of x dx. Now, one little parallel before we move on is if you think about it, the antiderivative of f of x, we could just call it f of x if we wanted to. Now, if we come over here, I'm just going to bring this over. So f of c is 1 over b minus a. And if the antiderivative of little f is big F, you could write this and evaluate it at b and then at a and subtract, which just gets you f of b minus f of a over b minus a, which you'll notice is actually just one derivative up from here. So that's kind of an interesting little connection in itself, but I'm not done with that just yet. That's a kind of very close parallel. If we take this b minus a and multiply it up to the other side, then we get what we understood about areas, that the area of the rectangle whose base is b minus a and whose height is fc, so the area of this rectangle here is equal to the area under the curve from a to b, which is this area here. So what I like about this comparison is that where the mean value theorem for derivatives guarantees equal slopes, the mean value theorem for integrals guarantees equal areas. And that brings us to the end of this lesson. I hope you found it helpful, and if you did, please do click like and or subscribe to my YouTube channel, Ready to Derive. Thank you.